Chapter 14 Partial Derivatives 14.1 We talk about functions of several variables. In this section, we study functions of two or more variables from 4 points of view. Remember, functions can be described verbally by a description in words or numerically by a table of values, algebraically by an explicit formula, or visually by a graph or level curves. First, we talk about functions of two variables. Now, consider the temperature of a point on the surface of the Earth. The temperature at that point is actually depending on the longitude and latitude of that point. So we can think about temperature as a function of two variables, x and y, where x here can be the longitude and the y here can be the latitude. So this is an example of a function of two variables. Another example of a function of two variables is the volume of a circular cylinder. It depends on the radius of the base and also the height of the cylinder, h. So the volume of this cylinder is a function of two variables, r and h. And this function here is given by this formula, which is pi r squared h. Volume is a function of two variables, r and h. So the two examples we had before, those are examples of function of two variables. The formal definition of a function of two variables says that it is a rule that assigns to each ordered pair x comma y in a set D a unique mu number denoted by f of x comma y. For example, for each given pair of longitude and latitude, we're going to get a unique temperature for that point. For each base radius r and height h, we're going to get a unique number for the volume of the circular cylinder. The output will be a unique mu number denoted by f of x comma y. The set D for all possible x comma y is called the domain of the function, and the range is the set of all output, all values that this function f is going to take on. Usually, we can write this f of x comma y as z. So think about this as z. When we write z equal to f of x comma y, we make explicit the value taken on by f at the general point x comma y. Now you see over here, the variable x and y, they are independent variables. And z, which is this f of x comma y, the z here is the dependent variable. These two are independent variable. And z is the output. It is the dependent variable. Now, here's one more example of a function of two variables in real life. So for example, in part of the world that the weather in the winter is very cold, we use something called the wind chill index to describe how cold that you actually feel. The wind chill index let's call that W, we can express that as a function of two variables. The wind chill index is a function of T, which is the actual temperature that you can read from a thermometer, and also V, which is the wind speed. So if the temperature is -5 degrees Celsius and the wind speed is 50 kilometer per hour, then you actually feel that the temperature is as cold as a temperature of -15 degrees Celsius with no wind, because the wind speed is kind of strong, 50 kilometer per hour. So you feel much colder than this actual temperature over here. So the function value when t is equal to -5, when v is equal to 50, is equal to -15. Next, we're going to talk about graphs of function of two variables. Here's a visual picture of a graph of two variables. And let's say the domain of this function is D, this orange shaded area over here on this xy plane. Then what does this function small f do? Well, it takes on every x comma y on this xy plane, and it assigns a unique function value, and that function value here, you can consider that as the z coordinate of this point in 3D space. Now, when you map every point in this domain by this function f, then you're going to get a connection of point in space, and the connection of those points in space is the graph of this function small f. So remember, in the past, when we have a function f of one variable, we get a curve with this equation y equal to f of x. For every x in the domain of the function, we get a unique y value as the output. Now, in function of two variables, the domain will be a set D on this xy plane. So think about this set D over here. That's the domain of the function. And then you're going to map this region D, map it to this set S over here in 3D. So for every x comma y down here, there will be a unique point here, x comma y, and the last coordinate z here will be given by this function value f of x comma y. Now, when you're looking at the graph, you can visualize this graph over here, and then casting the shadow down on this xy plane, and the shadow over here is the domain D in this xy plane. So imagine that this is like the cloud in the sky, and then the shadow down over here is the domain for the function, and this surface here in the sky, think about that as the cloud, that is the graph of the function. Now, if the function f of x comma y equal to ax plus by plus c, if the function is given in this form, this is called a linear function. Notice that the exponent on x and y here are both 1. And that's called a linear function. The graph of such a function, we have this equation either this way or this way. Remember f of x comma y, we can think about that as the third coordinate of that point in space. So we have x and y, and then the last coordinate z is given by the function value f of x comma y. So we place this by z. We can write this equation z equal to ax plus by plus c. Or if you move everything to the left side and leaving the other side to be 0, you can put it this way: ax plus by minus z plus c equal to 0. The graph of this, as you recognize this already, we had that before. This is an equation of a plane where x, y, and z, the exponent here on them, will be 1. Those are equations of a plane. The graph of them will be planes. Now, linear function, this is a linear function of two variables, and it plays a central role in multivariable calculus. So it's worth remembering. Next example, we're going to sketch the graph of this function. The first thing we do to sketch this graph over here, we're going to replace this g of x comma y by z. So z is equal to this. After that, we're going to square both sides. Square both sides giving us z squared equal to 9 minus x squared minus y squared. And if we move all the variable to the left side equation, we get x squared plus y squared plus z squared equal to 9. Now, after we put it in this form, and this reminds us of a surface. Now, what kind of surface does this remind you? Remember, the standard equation for a sphere is x minus h squared plus y minus k squared plus z minus l squared equal r squared, with center h, k, l, and radius r. So this equation here, comparing to this standard equation for sphere, we know that the center will be 0, 0, 0, which is at the origin, and the radius will be 3. Now, because z is equal to the positive square root of this quantity, z cannot be negative, so we don't have the lower part of the sphere. So z will be greater equal to 0. So we have this upper part of the sphere. Now, what's the domain for this function? Now, remember, when we try to find domain of an even root function, it is required that the quantity inside the square root, inside this even root, has to be greater than or equal to 0, which is equivalent to x squared plus y squared is less than or equal to 9. X squared plus y squared is less than or equal to 3 squared. We know that x squared plus y squared equal to 3 squared is this circle centered at the origin with radius 3. So this region with this x squared plus y squared less than or equal to 3 squared will be the inner region of the circle. Because the equal sign, we also have this boundary including this circle. And as you can see that the graph of the function is this half sphere, and think about this surface, this half sphere, is going to cast a shadow on this xy plane. That shadow will be that circle on this xy plane, which is this circle here. It is a circle centered at the origin with radius equal to 3. The circle and including the inside of the circle will be the domain of the function. So think about that as the shadow of the surface on the xy plane. Next, we're going to talk about level curves. Level curve is just another method to visualize functions of two variables. So think about we have a surface in this 3D. So we have the surface. Think about this as a graph for some function. And then it's going to cast a shadow on this xy plane. The shadow that this surface casts on this xy plane, that's the domain for the function. Now, let's call that function f. Now, you're going to set that function value to be a constant. For example, looking at the graph over here, if you set the constant here to be 20, so if you're going to set this z here to be a constant, say 20, so the z coordinate will be 20 for every point on this horizontal trace. If we cast that horizontal trace down to this xy plane, we'll get this level curve on this xy plane with k equal to 20. And that's called the level curve f of x comma y equal to 20. Similarly, if you let z to be a different value, for example, you let z to be 45, and then you cast every point here on the survey down to this xy plane, and you get this curve. Then this curve over here is the level curve f of x comma y equal to 45. So you can get different level curve by setting this z here to be different constant. So letting z to be different constant k, say k equal 20, 25, 45, we get different level curve. So you can see level curve are on this xy plane. And think about that, it is the projection of those horizontal traces onto this xy plane. Here is another example of level curve. You see those level curve occurs in topographic maps of mountains. So z equal to 20 is this horizontal plane over here, z equal to 20. And think about that, you use that horizontal plane over here, z equal to 20, and you slice this surface. When you slice that surface, you get this curve over here. This is the horizontal trace, one horizontal trace of the surface. And then you project that trace right here, this horizontal trace, onto this xy plane. You get this level curve. And then you can take another horizontal plane, for example, say z equal to 45, and you're going to use that to slice this surface, and you get this horizontal trace. When you project this horizontal trace onto this xy plane, you get this level curve right here. And vice versa, if you go get those level curve here on this XY plane, you can get back this surface over here by lifting those curve here to a high. So for example, for this level curve over here, k equal to 20, so you can take this curve over here and you lift this up 20 unit to the positive z direction, 20 unit up, and then you get this horizontal trace. And then you will take another level curve here, and here k is equal to 25. You're going to lift this level curve up 25 unit, and you're going to get this horizontal trace. So for every level curve here on this xy plane, you're going to lift that up. Depends on what this constant k here is equal to. By doing that, you will get back the traces of this surface, and then you can mentally piece together how the graph look like. One thing that you might want to pay attention here is that you see the surface is steep when the level curves are close together. So here you see here is 20 to 25, 30 to 35. So the k here are separated by 5, are incremented by 5, right? And if the level curve here are close together, for example, like over here, they're kind of close together. And over here, the level curve are further apart. When the level curve are close together, that means the surface is steep. For example, from here to here, you see the surface is actually steeper. And from here to here, you see the surface is actually somewhere flatter. It's not as steep as this part right here. So when the level curve are further apart, they are not as steep as those places where the level curve are closer together. So the spacing of the level curve indicate the steepness of the graph. Here you can see that the surface will be steeper, and here you see the surface will be flatter because the level curve are further apart. So when you look at those map of mountain regions, this is one, by looking at the spacing of those level curve, you can tell the steepness of the mountain. And you see that level curves are curves of constant elevation. See, k equal to 45, then the elevation here will be 45. And if you walk along one of those contour line, so this is contour line right here, then you are neither ascend or descend. You're not going up or going down. You are at the same level. The elevation here remain as constant. Another common example is the temperature function. The lower curve are called isothermals and join location with the same temperature. So here is a weather map of the world indicating the average July temperature. So the isothermal are the curve that separate the color band. So you see those are level curve right here. So 80 degree along this curve, 40 degree along this curve. The graph that contains all those level curves is called a contour map. Sometimes a contour map is more useful than a graph. This is a computer generating contour map with the corresponding computer generating graph. So you see we have this graph over here, the level curve for this graph will be this. And this is just two different views of the same function. When you rotate them, you see from this angle or from this angle. As you can see here, the level curve here are dense. You see the graph over here is steeper. And here the level curves here are further apart. And you see the graph over here is flatter. Similar to this one, over here, the level curve here are very close to each other. They are crowded together near this origin. And you see near this origin, the graph is very steep. When it's away from this origin, you see the level curve are further apart, and you see is flatter, right here and here. Next, we're going to talk about functions of three or more variables. A function of three variables. Well, we have function of two variables. Now we just need to add one more variable. So before we have function of two variables, now we're going to talk about functions of three variables. Just add one more variable here. X, Y, Z in domain D, which is a subset of R3. And then what does this function do? It takes on every X, Y, Z in this domain and assign a unique real number, and that unique real number is a function value f of x, y, z. Well, let's think about some example. So you have a temperature at a point on the surface of the Earth. So think about the T here as a temperature. Think about this x over here as the longitude. Think about the y here as the latitude, and the T here as the time. So the temperature of a point on the surface on Earth, it depends on the longitude and latitude of that point, and also depends on the time. So the temperature is a function of three variables, x, y, t. So that's an example of a function of three variables. Next, let's try to find the domain of a function of three variables. This is a function of three variables, x, y, z. It's given by this expression. Well, this expression here is defined. But before we find the domain of this function, let's review basic step to find domain. So if you have a quotient, it is required that the denominator does not equal to 0. And if you have an even root function, then you would like to have the expression inside, which is called radicand, to be greater than or equal to 0. Equal to 0 is also okay. If you have a log function, say ln or base a log, then it is required that this quantity here inside this log has to be strictly greater than 0. So here is a ln function. So it is required that this quantity to be strictly greater than 0 in order for this to be defined. If it is equal to 0 or less than 0, then ln of that is undefined. So we need this quantity to be strictly greater than 0. And what about this part over here? Well, x times y is a polynomial in x and y, and sine of z is a trig function. For sine, there's no restriction on this in order for this to be defined. So actually, it could be all real number, but that will be no restriction from this. So the only restriction will be z minus y to be strictly greater than 0. And when you solve this for z, you have z is strictly greater than y. So the domain for the function here will be all x comma y comma z, which is a subset in R3 that has to satisfy z strictly greater than y. So the way that you read this is the domain is the set of all x, y, z belong to R3 such that z is strictly greater than y. So before we have function of one variable f of x, and then today we talk about function of two variable f of x comma y, and then we talk about function of three variable f of x, y, z. Now we can actually keep on going. We can have function of four variables. We can have function of five variables, etc. Now for function of three variables, you see the domain will be in R3, and then the output will be, you need one more dimension. So you need to have a four-dimensional space in order to visualize the graph for f of x, y, z. So it's very difficult to visualize function of three variables because that require three dimension plus one dimension. So you need four-dimensional space to visualize that. However, we can actually visualize a function of three variables by examining its level surfaces. We call that when we try to examine the graph of a function of two variables, we examine its level curve. When we try to gain insights of this function of three variables, we examine its level surfaces. Extend level curves by one dimension, we get level surfaces. How do you find those level surfaces? We can let this w here to be different constant. For example, it could be C1 or C2 or C3. So we let this w here to be C1 and then C2, etc. So you say w to be C1, you get this surface, w equal to C2, or C2 here, you get this surface. You let w to be C3, you get this surface. And by letting this w here to be different constant, we get different level surfaces. When we put those level surfaces together, we have a better idea of how this function behaves. And one suggestion here is for the four dimension, you can think about this, like maybe the x, y, and z will be maybe the coordinate of the point in space. And then the w here, think about that is the temperature at that point. So for every point in this three-dimensional space, you get a different temperature. Or you can think about the w here as the density of some object. Think about x, y, and z. Those are the coordinates of the location of the object in space. And w is the density of the object at that location. Notice that when the point x, y, z move along a level surface, the output w, the value of the function w, will stay the same. Now we have function of two variable, function of three variable. We can have function of four variable or more. So a function of n variables is a rule that assigns a number, let's call it z, to an n tuple of real numbers. This n tuple here is x1, comma, x2, dot, 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 all the way to xn. So what does it say? So that means it takes on every x1, x2, all the way to xn and assign a number to that n tuple. Rn stands for the set of all those n tuples. Let's try to relate this to an example in real life. For example, you're going to make a food product. So the cost of making that food product depends on the ingredient, the cost of each ingredient in that product. Say you have n different ingredients in the product, and each ingredient here have a different cost, say different price. Say C1 is the price for the first ingredient, C2 is the price for the second ingredient, and then Cn will be the price for the n ingredient. Then the total cost here is a function of this n ingredients. The domain of this function, it is a subset of Rn. And sometimes we use the vector notation to write such function in this compact form. So this ball face x here, it stands for a vector that has n components, x1, x2, all the way to xn. And then we can write this function of this vector x in place of f of x1, x2 to xn. Now when we do that, this function of x1, x2, all the way to xn, which is equal to c1x1 plus c2x2 plus cnxn. We can write that as the dot product of two vectors. The first vector c has n component, c1 all the way to cn. And then the x vector, we have n component also, x1, x2, all the way to xn. This is a dot product of this vector and this vector. And you see this vector over here is a vector in Vn, a set of all vectors in n dimension. So this is a vector in Vn. So we have three ways of looking at a function f defined on a subset Rn. So you see this function here, the domain of this function here is a subset of Rn. We can think about that as a function of n real variables, x1 all the way to xn, like that, or as a function of a single point variable. Well, we can think about that point as has x coordinate x1 all the way to xn. Or you can think about that as a function of a single vector variable, x, that has n components.